All right, good morning, everybody. Welcome to your last human anatomy class of the week. Yeah, I know. Mixed response there, huh? All right, we're going to continue today with the appendicular skeleton, specifically the lower limbs. You can see an example here. This is a radiograph of a hip replacement. Pretty cool there. You can see how they lop off the top of the femur and they replace it by pounding the titanium rod into the proximal end of your femur, and they drill out the acetabulum and put in this cup and put in a fake ball there, and there's a giant screw. And you can compare that to an intact proximal femur there. Kind of neat. Just wanted to share that. Today, but in advance of today's class, you had a class program that was pretty minimal if you had done the reading for Wednesday. It was just kind of making sure you got stuff done and we're up to speed. Today's class is an exciting mix of activities. We are going to review your ticket out question from Wednesday. Just want to make sure we've got that information straight. And then we'll do some drawing. As you probably suspected, we're going to continue on with the lower limb today and work through that. Yet another activity to make sure you got stuff. Got all kinds of stuff. I got a video today on knuckle popping because this question always comes up. There's a nice short video kind of explaining what's going on with that. And then I've got a couple announcements and your Friday Venn diagram to wrap things up. So before we dive into that, what questions do you have? Oh, a few of you asked me about weekend access to the lab. I'm going to, Hannah's going to send an email, remind me, and I'll make sure that the door is open. Also, if you want to work in there, I have it set right now to be open until 9 o'clock p.m. If you need to get in there later, just email me, and I actually can give you the door code as well. If you're not a science major, you don't have swipe card access to the building, again, just email me, and I can arrange that for you as well. So if you need access, just let me know, and we'll make it happen, basically. So let's talk about your ticket out from Wednesday. So the question was, with what bones does the humerus directly articulate? And I wanted to go through this and make sure we've got a good understanding of that. So remember, the humerus is the only bone in the brachium, or the forearm, or the upper arm rather. And it articulates in the proximal end with your scapula. Remember, that's where the head of the humerus articulates with that shallow cavity called the glenoid cavity in the scapula. And about 2/3 of you picked scapula. And then at the distal end, it articulates directly with both the radius and the ulna at the elbow. So all of you picked ulna. Most of you got the radius. But just remember, if I ask you with what bones does a bone articulate, make sure, especially those limb bones, you're thinking about both ends of it. Just want to make sure we've got this clear. Remember, it does not articulate the lunate or the scaphoid. What bone of the antebrachium articulates with the lunate and the scaphoid? The radius, good. And then a few people pick clavicle as well. Remember, the clavicle is your collarbone here. The collarbone articulates medially with what bone here? The manubrium of the sternum, right? And you can feel that if you put your finger right here. Go ahead and move your arm. You can feel that. It's a joint you don't think about very much, but it's actually a really important joint and really flexible because you can rotate it and you can bend it as well. So it does all kinds of stuff right there. You can feel that. And then the clavicle articulates laterally with what bone? Scapula. Yep, specifically what part of the scapula? The acromial process. Good, good. Any questions on that? Hip bones connected to the knee bone, etc. Oh, and I have this diagram here actually just to illustrate that. So just going back to the humerus, remember that proximally it articulates with the scapula and distally with the ulna and the radius. And it's a diagram that I've showed you before. All right, that's thinking about the upper arm. Let's transition and just refresh your memory about the pelvic girdle. We're going to do a quick 2-minute review activity. So as best you can from memory, so don't look at your notes yet, draw and label a diagram of the left coxal bone from a lateral view and label everything that you can possibly think of. And be sure to label the anterior and the posterior bone. I'm not going to lie, this is really challenging because the coxal bone has this weird shape. Try to do it as best you can for a couple minutes without consulting your notes, and then we'll go back and look at your notes and make additions and everything like that. But do the best you can before looking things up. And I will collect this at the end of class. So part of your ticket out, I'll get an image of this from you. All right, that's 2 minutes. Now go ahead and take a look at your notes and amend or add to your diagram as much as you can. You feel free to work with each other, share ideas, check each other's. That's totally fine. Take a couple minutes, make sure you've got that. Make sure you've got the right bones in the right direction too.
Wait, I want to know that.
All right, so you've got a chance to look at your notes now. Let's bring it back here and I'll show you a diagram. So I asked for the left coxal bone from the lateral point of view. So this is going to be anterior in this direction. This is posterior. To walk you through a couple important pieces I want you to make sure you have on your diagram. I'll just start down here, the ischial tuberosity. Remember, this is kind of like a bulbous, rough feature. This is where you put your weight when you're sitting. So all of you right now have most of your body weight on that. If you put your hand underneath your bum, you can feel that bone quite prominently. This is the attachment point for your hamstring muscles as well. We'll get to that a little later, but I just want to introduce that topic or that idea. We have the obturator foramen. This is the big hole here. And remember, that is formed by a combination of the ischium, the inferior and posterior part of the coxal bone, and the pubis, which is the inferior and anterior part of the coxal bone. Remember, you have this cup right here called the acetabulum, which comes from the word for vinegar, because it's like a little cup they used to serve vinegar in, which would be weird if you serve vinegar in a hip bone, but whatever. Remember, this is the cavity. This is a deep socket where the head of the femur articulates. And we'll talk about that articulation, actually the first thing we're going to talk about when we get into lecture today. Here in the posterior, you have this greater sciatic notch. This is where the sciatic nerve passes through. And the upper part of the coxal bone is known as the ilium. We have the ala, which is the wing. It's not labeled here. The iliac crest is this crest that goes superiorly across the ilium. And we have anterior superior iliac spine is the kind of anterior part of that crest where it becomes a little bit narrower. There's some other features on here too, but these are the main ones that I want to make sure you focus on and you've got. What questions do you have?
Which one did you say was the attachment point for hamstring?
That is the ischial tuberosity. Great question. So which of the three parts of the coxal bone articulates with the sacrum? Just yell it out. Ilium, good. Remember, you have two articulations on either side with the sacrum, and that is, well, you can't really see it here, but it would be on the other side of this part of the ilium. And which part of the coxal bone articulates with the other coxal bone? Pubis, yep. You have the two pubic bones, or the two pubis parts of the coxal bone articulate anteriorly at the pubic symphysis. We talked about that the other day. Just to review, make sure you got this. Any questions on that? Cool, and we'll look at those bones in lab this coming week as well. So let's continue with the appendicular skeleton. Oops, I didn't want to do this. Hold on, let me skip ahead here. I meant to black out these slides, but that's okay. Covered this. Okay, I want to talk about the lower limb. So the lower limb is your legs, right? And it's important for a number of reasons, one of which is that it carries the entire weight of the erect body. So you are all sitting now, so a lot of your weight is on the ischium, or the ischial tuberosity, as I mentioned. But when you're standing, all of your weight goes down your legs, not terribly surprising. But because of that, these bones are thicker and stronger than those of the upper limb. Now, you could think about other related mammals that are four-legged. They don't have as strong of this differentiation between upper and lower limbs as we do, because we're bipedal. And our limbs, those limbs do very different tasks most of the time. We can divide the leg into three segments. We have the thigh, which is also known as the stylopodium. We have what's called the leg, or the shank, or the cruce, which is called the zygopodium. And then we have the foot, which is the ankle and the foot together, right? Now, it's confusing because technically when I talk about a leg, I just mean from the knee to the ankle. I just mean this section here. But in common parlance, we refer to the leg as the whole thing. I usually avoid using this term in the anatomical sense because I find it confusing. And in fact, I generally stick to either thigh or stylopodium, or just zygopodium here, or lower leg, I'll say sometimes. So the terms that I generally use are stylopodium and zygopodium. And the reason for that is actually because we measure these parts of the limb on our lizards, and we refer to them as that on the lizards. So I just kind of default to using that here. But just be aware that in the anatomical sense, the leg is the same as the shank or the cruce, and that's just this part of the limb. Let's start at the top and work our way down. So I mentioned I'd talk about this cool joint at the acetabulum of the coxal bone, and that is the joint between the head of the femur and the coxal bone. A couple things I want you to know here is that we've got this ball and socket joint. We're going to learn a little bit more about joints in lab coming up this week. But there's a feature on the head of the femur called the fovea, this kind of indentation rough spot. Kind of looks a little bit, if you took that part off, like the Death Star, where you got the little ray thingy that blows stuff up. I don't know what they call it. What's it called? Does it have a name? Big ion? Is it ion cannon or something like that? It's got a name. You know what I mean. So anyway, that is the attachment point for this ligament that binds the head of the femur into this cup of the acetabulum. And that is called the Fovea Capitis. That is this really strong ligament, and it basically holds it together and anchors that joint. Now, I mentioned that joint is also very deep, and so that gives it stability as well. But there's a lot of weight on that joint. When you're standing, for sure, but especially when you're doing something like running or jumping or landing, all of that weight from your upper body is transmitted through that one joint that needs to not only support that weight, but also needs to bend and be flexible. Think about jumping and landing. You're putting all your weight there, but you're also bending it at the same time. So it's got this really tight fit between the head of the femur and the acetabulum, and furthermore, it has this cool internal ligament here that binds it together. Yes?
I have two questions.
Two questions, okay.
So first, does this joint have a special name associated with it, or is it just like...
Oh, it is the, what is the name of the joint? It does, and I'm blanking on it right now. Sorry, it's like the femoral acetabular joint, I think.
Okay.
It's not coming to me, but let me look in the book and see. Here, actually, let me look right now. I should know that. Sometimes the words just aren't there. I don't see it. That's probably why I'm blanking, is because I don't see a particular name for it, which is a little surprising. I'm sure it has one.
Your name's on.
Yeah. Okay. Let me get back to you on that one, okay?
Alright.
Second question.
With the last slide, what, do you know the group meaning for Stylopodium and Zygopodium?
No, stylo generally refers to like a long, thin projection. Like the word pen actually comes from that same root. Stilo. Is that Spanish? No, French. French is stilo. Yeah, thank you. But Zygopodium, I don't know. That's a good question too. I was actually wondering that myself recently. It's just called the hip joint. I'm gonna call it the hip joint. It's a joint that likes to wear skinny jeans and drink craft beers and listen to obscure indie rock. Lots of noise in it. That's what hip was like 20 years ago. I don't know what hip is anymore. Is it the same stereotype? Brooke, go ahead.
So with the hip being attached, like with the head of the femur being attached to the hip with the ligament, when you like dislocate your hip, is that like arm the ligament, or is it flexible enough to kind of allow it to be like dislocated and like off back?
Great question. The answer is kind of yes and. Like it can be both depending on how severe it is. It can break that ligament altogether, or it can kind of stretch it out, or not necessarily break it altogether, but like get a tear in it. And so, yeah, it can be anywhere kind of in between there. Often when you hear about someone getting a falling, especially older folks, falling and breaking their hip, it's actually the order of those events is usually the opposite. What happens is because of osteoporosis or other aging related loss of strength in the bone, what happens is actually the bone actually breaks and that causes the person to fall. Rather than, often we think of it as like someone falls and the impact is what breaks the bone, but usually it's the break that then causes the fall. That was not really related to your question, but sure, go ahead.
So if this ligament were torn,
yes,
would the correction be just like stitching it together, or would they have to like do some kind of a graft?
Could they reattach it? I don't know. Yeah, that's a good question. I don't know. I do know that when they do hip replacement, like you saw at the opening slide, there's no ligament in that case. It's just the ball and socket.
Super smooth.
Yeah, and you can actually, it increases your chances of getting a dislocation for that reason. Like there's certain ways that you're not supposed to bend your hip, because I know this very well. There's certain ways you're not supposed to bend your hip because you could risk dislocating it, because you don't, part of the reason you don't have that ligament. So yeah, I don't know. I don't know if it's essential to replace it, or you can, how much of it grows back on its own over time. I'm sure. These are good medical questions, and yeah, the medical part of it I'm not as familiar with, so. All right, let's talk about the femur then. So let's get into some detail. Here is a femur from an anterior view on the left and a posterior view on the right. Working our way from superior to inferior, we can see the head of the femur is that ball-like feature. The Fovea Capitis is the rough spot at on the head where that ligament attaches. We then have the neck between the head and the rest of the femur, and then we have these features called the trochanter. We have a greater and lesser trochanter. I'm going to use this guy. I've never used this in class. I'm totally going to use this thing instead of I'm always like jumping, but we've got the greater trochanter, which is this spot here, and the lesser, which is this spot down here. Those are the only place in the body where we have this feature on a bone called the trochanter. Between them, we have the intertrochanteric line, which is kind of this line that goes right here. A couple other features that are important. We have the greater gluteal tuberosity right here, and that kind of transitions down in the middle of the diaphysis here to the linea aspera, and this is the attachment point for muscles that we'll talk about in a little bit. And then that linea aspera kind of splits and becomes what's called the supracondylar lines. One is medial and one is lateral. Is that right? Yep, medial, lateral. And then on the bottom here, we have this. We have a lateral and a media condyle. These are these kind of big bulges at the end, and in between them, we have a smooth area called the intercondylar fossa. And then on the flip side, on the anterior side, we have this very smooth area called the patellar surface. And you probably saw this in lab. It's that smooth area on the distal end of the femur where the patella basically slides across that femur when you bend your knee. So a number of features here. I'm introducing it. We're going to, again, talk about this in lab in more detail. Let me see if oh, and going back to the broken hip thing, it's this neck that's basically right here. That is kind of the weakest part of the bone. And so when you hear about a broken hip, it's generally a break somewhere in this area because the weight from your body is transmitted on this head, and then it kind of has to transmit laterally here, and you put a lot of pressure on that part of the head of the femur. We talked about in lab, you saw a transect through a femur, and you could see the spongy bone inside. And remember, those trabeculae form in a certain pattern that best deals with the stress of that weight distribution. So just to make the connection between what we saw in lab and what we've got going on here. And there's lots of bumps and features on the femur that are attachment points for muscles. We'll talk about some of those in more detail. We're not going to cover all of them in this class, but there's a few major ones I want you to know. Specifically, the Gluteus Tuberosity, this linea aspera, and then the medial and lateral supracondylar lines.
So if what we call a broken hip is just a broken neck of the femur, what do you call it when you break, like, actually the coxal bone?
Do we actually break the coxal bone itself? I don't know if it's a coxal bone fracture. I don't know if it has a specific name. Much less common than breaking the head of the femur, for sure.
So it's a weak part of strongest bone.
It's the weakest part of the strongest bone. Yep, that's a good way to think of it. You've got all that weight from your body going right through that.
So are people using them in ways they shouldn't, or
The
like why the prevalence
of that fracture?
Injury in the strongest bone?
Because it's the strongest bone, but it's also the greatest weight-bearing bone, right? And so because it bears so much weight all the time, it's under stress, and it has to be strong to respond to that stress. But if it's over for aging or osteoporosis or whatever, it loses that strength, and you still have that weight. Like, the weight doesn't diminish necessarily, and so you get a mismatch between how much pressure is on it and then how strong the bone is.
So you would say most of the injuries are age-related?
To this?
Yeah.
Generally speaking, yeah. I mean, most of anything with your body going south is going to be age-related, right? But it can be. It can also be just something that happens over time. Like, osteoarthritis is when that cartilage just kind of wears away. That can happen, generally as the older you get, the greater chance of that happening, but it can happen when you're younger too. So. And you can get, there's ways, there's congenital malformations of the bone too, if you're born, and actually we'll see some of that coming up. You could be born with like something called a club foot or something like that, that can be corrected when you're young. So, yep, yeah. As you get older, your body goes south. It sucks. Not gonna lie about that. All right, let's look at the femur here. So I mentioned that there are several structures in the femur I wanted you to pay close attention to. And these are the ones. So make sure this diagram is important. These are the features that I'm going to focus on and ask you about. I've mentioned all these previously. I just want to put it in a specific slide. Please note that I just cut the femur so it fit on the sheet here, or the screen here. The diaphysis continues down, so I just kind of removed part of the diaphysis where there weren't important structures. So make sure you got the greater and lesser trochanters, the gluteal tuberosity, the linea aspera, and the medial and lateral epicondyles. We'll talk later about the muscles that attach, but just to kind of orient you a little bit to it now, your gluteus maximus, the largest, strongest muscle in your body, inserts right here. So this is the posterior view of a femur, and it inserts there. And then also it has its origin up on your coxal bone. So that's your big old butt muscle. And you've got the linea aspera, your pectineus, which is a smaller muscle in that same area, kind of in your hip region there, inserts there. Down here on these medial and lateral epicondyles, you have your gastrocnemius, which is your calf muscle, right? And so that inserts up here on your femur and then extends down into your heel, and you'll see that. So make sure you've got a good feel for those landmarks on the femur, not only for understanding the femur, but that will be important when we talk about muscles and the insertions and origins of muscles. This would be a great exam question. I could say, draw me a posterior view of the right femur and label the following things. And I would say these things, and then you would draw something that looks like this and label those things. It's important to know, think about left, right, posterior, anterior too. So is this a right or a left femur? Oh, this is controversial. Well, is it a posterior or an anterior view? How do you tell that? It's posterior view, right? Because here we would have that smooth patellar surface. Instead, we have that intercondylar fossa right here. And so you're looking at it from behind. And if you're looking at it from behind, then you know that this neck and the head are bending in this way. It's got to be a right femur from behind. So it's a right femur from the posterior view. So make sure you can orient yourself to those bones as well. I like to ask questions about left or right, posterior, anterior, specifically for the femur and the humerus as well. So let's look at, what do I want to do? Yeah, I got a little more here. I want to talk about, why my diagram just, what is going on here? It's going to be a fun class. Look at all of the pictures just disappeared from my presentation. That looks like a complicated one too, huh? That's so weird. All right, give me 1 second, please. I'm not sure what happened. Most curious. Nope. Anyone ever had this happen before in a PowerPoint? Any tips? Close everything down and restart it. It's always the best advice, right? Sorry, bear with me for 1 second here as you collect your notes. What time we got? Okay.
You have to down 2 points because your presentation wasn't ready.
Yep, I lost 5 course points today. Sucks, I'm down to a B-. You just put that in the evaluation at the end of the class. Okay, that works. We saw that one. All right, boom, here we go. Great, thank you. All right, so I want to mention too, we've talked about the parts of a long bone. Specifically, we talked about the diaphysis, which is the shaft, and the epiphyses, which you have a distal and a proximal epiphysis, and that's the end of the bone, also known as the head of the bone. We also have a transition region in between the diaphysis and the epiphysis. And I didn't talk about this in lab, but I want to introduce it now. It's called the metaphysis. So it's basically just that small section in between the shaft of the bone and the end of the bone, the epiphysis. Now, we talked about growth plates or epiphyseal lines in lab. On the femur, you can see this, these clearly during development. We had some examples in lab. I had some cow bones where you can see this line. Note on the distal end, we have this growth plate that's more or less running horizontal. But on the proximal end, we have 2 of them because the bone is kind of growing off at 2 different angles. We have an epiphyseal plate between the greater trochanter and the main part of the bone here, and another one between the head of the bone and the head of the bone and the metaphysis there. So you kind of have 3 growth plates on your femur. And again, these are places where the bone expands when you're growing, and so it's cartilaginous when you're young. And then when you get somewhere in your late teens or early 20s, by that point, your bones aren't growing anymore. You don't get any taller, and those eventually fuse. And if you look at a mature bone in lab, as we saw, you can't really see any remnant of that epiphyseal plate. Essentially, it's just entirely bone. You can't even really see a line there or anything. It looks like it never happened. But when you're young and those bones are developing, you can see that very clearly because there's a line between the 2 bones because the cartilage doesn't preserve. Let's keep moving down to talk about the kneecap. We talked on Wednesday about sesamoid bones. This is the big and arguably the most important sesamoid bone in your body. It's embedded in this tendon that secures the quadriceps muscles. So your quadriceps muscles are these muscles on your stylopodium here, on the anterior part of your stylopodium. They are big, strong muscles. Specifically, the rectus femoris there is a big old muscle, and that attaches to the tendon. Attaches to a tendon which runs. Basically, the patella is embedded in that tendon, and then that attaches to the anterior tibia. So it basically runs right over that knee joint. And the patella is important for a couple reasons. One is that it allows that muscle to get extra leverage across the joint, which gives you extra strength and speed. Secondly, does it give you? Yeah, it would give you additional speed as well. And also it acts, I like to think of it as a little knee helmet. It protects the knee. Knee is a very sensitive joint, and also can be very prone to injury, as you've ever seen. You know, when you're doing things in the world and you fall, generally when you fall, you're going to fall on your knees. And so this provides that extra protection from the joint. I'm not going to ask you too many details about the patella. I would like you to be able to identify the anterior and posterior surface. You'll see in lab, it's really obvious. The posterior surface is really flat and smooth, again, because that's where it's articulating with that distal end of the femur. The anterior is very rough, and that's because there's attachments for the tendons across there. I think that's all I want to say about the patella.
So does that mean that if you, because there's patella replacements, right? Or like knee.
Well, there's knee replacement, but generally, what do they do with the patella? Generally, they're going to preserve the patella if they can.
I was going to ask, if you then were to remove that, replace with an artificial one, would that weaken all the muscles that connect with it?
I'm sure it would. Anytime you injure or cut a ligament or a tendon and it has to heal, it's going to be weaker, like no matter what. And so I don't know exactly what that process is like, but I can't imagine you could replace anything and have it not be weaker. Bless you. You can feel, of course, you can feel your patella very easily in your knee. It's commonly called your kneecap there. All right, let's move down and talk about the zygopodium, also known as the leg, also known as the shank, also known as the crus. This is your lower limb from your knee to the ankle, and it's composed of two bones on either side. Yes, question, sir. Yep.
Why is this much pain when someone, like, for example, dislocates a patella? It's like a protection mechanism.
Well, you're moving it out of joint, so it's there's going to be a lot of pain. But I guess my thought on that would be, like, imagine if instead of your patella getting knocked out of joint, your whole knee got knocked out of joint. Like, you'd much rather, even though your patella is like taking one for the team in that sense, right? And so you can think of it as like basically doing its job by protecting the knee joint, even though the patella is going to get damaged.
Mm-hmm. Is there such thing as someone not having a patella, like if they take it out because they're causing someone so much pain?
Oh, I don't know if they'd remove it entirely. Could you not have a patella? I don't know the answer to that. Yeah, that's an interesting question. They'd remove it. I'd be surprised if they removed it entirely without. I'd be surprised if they removed it without replacing it somehow, but I don't know the details of that. Yeah, we got to get an orthopedic surgeon in here to answer all these great questions. Like, these are fantastic questions. I just don't know the details of those procedures. So, let me see. What time do we got? I want to show the video today. Yeah, we'll stick with the video today. Maybe I'll skip the other activity and show the video. So let's talk about the leg, the lower limb. We've got two bones here. The tibia is medial and the fibula is lateral. The tibia is the big boy. This guy is bigger. It holds most of the weight and does most of the work. The fibula is this stick, like really long, skinny lateral bone. It's important to note that it's not technically part of the knee. It articulates with the tibia proximally, but it does not articulate with the femur or with the patella directly. These guys, like the bones in your antebrachium, are connected by this interosseous membrane that keeps them kind of bound tightly together. Also, a homologous structure to the antebrachium. These bones have two joints, a proximal and a distal joint. And in this case, they're very, very tightly bound, and there's very little movement in those joints. Unlike the proximal joint, for example, of your radius and ulmus that we looked at, where the proximal end of the radius has that kind of disc-like head and it rotates against the ulna. Here we don't see very much movement at all. And get into a little more detail here. This slide might be a little overwhelming. Here's what I want you to do in this slide. I want you to focus on the aspects of these bones that are in big, bold letters, right? So I want you to be able to identify the head of the fibula, and of course the head of the tibia too. This feature right here is really important. So this is your anterior view of your right leg. So it's like looking like this. You have this tibial tuberosity, and if you feel, you can probably feel when you're sitting, just go below your kneecap, and you can feel like a nice big kind of wider rough spot right there. That's your tibial tuberosity. That's where the insertion of your quadriceps muscles are. So that's an important spot where those muscles are pulling when you flex your leg, right? We also have these important features called the malleolus. You have one on either side. You have a lateral and a medial malleolus. This is like those balls on your ankle. I got shoes on today. Most of you are probably not barefoot either, unless anyone has flip-flops on. This is what forms like those bulges on the side of your ankle. One of them is formed laterally by the distal end of the fibula, and one is formed medially by the distal end of the tibia. We'll talk about this in more detail when we get to the ankle joint, but notice how together these malleoli form this kind of clamp structure, right? It's this structure that allows your ankle to move really well in this plane. It's called dorsal and plantar flexion, up and down, but not so well side to side. You can move it a little bit for sure, but it doesn't move that well side to side, and that's because these two, the medial and the lateral malleolus, hold it in that clamp-like fashion. It gives you really great range of motion in one plane, but not so much in the other. Anyone who's ever broken or twisted or sprained their ankle knows that pretty well. If you push it too far laterally, it sucks. That's a technical term. There's some other aspects here as well that I won't get into right now. I'll save some of these details for lab. So for right now, just know these bigger terms, the terms that are in the bigger typeface there. You can see here the tibial tuberosity. I like the actual image as well. This big rough spot right here, just distal to the head of the tibia. Yeah,
Are they, because I don't know why, but I've always thought about them as like the tibia being in front of the fibula, not like with the tibia being posterior. Are they on the same plane, or is there a slight distance in between?
Exactly. So the tibia definitely extends anteriorly a bit more, and you can feel that in your leg. And you can run your finger down your tibia right here, and then if you feel laterally, it's actually a little bit hard to feel the fibula because there's a muscle that runs right here, but it is a little bit posterior as well. Your tibia will be kind of more in front, I guess you could say. Down here at the ankle, they're kind of more symmetrical. All right, I'm going to skip ahead. I have a short video I want to show today that's on knuckle cracking. I was going to do it after we talked about the hands and feet a little bit, but I'll just go ahead and talk about it now. It's going to introduce some terms that we haven't gotten to yet, but that's okay. It's just an introduction to it, and I think it's an interesting video. The question always comes up in class about cracking your knuckles. So let me go ahead and play this, and then I've got a few other announcements, and we'll wrap things up. Bless you.
What's that sound? Depending on whom you ask, the crackle of popping joints is either the sound of sweet relief or the noxious tones of a stomach-turning habit. Really though, what's that sound? I mean, why does bending your joints in a certain way make them pop like that? Scientists have offered several explanations, including rapidly stretching ligaments and, in severe cases, actual bones grinding against each other. But the most common explanation for why your stretched out joints sound like bubbles popping is that, well, there are bubbles in there. The joints in your fingers are the easiest ones to crack, but many people also crack the joints between vertebrae in their neck and back, and even their hips, wrists, shoulders, and so on. All these joints are flexible ones in your body. The space between the two bones is filled with a viscous liquid, synovial fluid, which contains long, lubricating molecules like hyaluronic acid and lubricant. Synovial fluid is more or less the texture of egg yolk, and its primary purpose is to cushion the bones and help them glide past each other. It also contains phagocytic cells that help clean up any bone or cartilage debris that ends up in the joint. But the reason it's important for knuckle cracking is that, like other fluids in your body, it contains lots of dissolved gas molecules. Knuckle crackers know that to get that satisfying pop, you stretch the joint farther than it normally goes, by bending your fingers backwards, for example. When you do that, the bones move away from each other. The space between bones gets bigger, but the amount of synovial fluid stays constant. That creates a low pressure zone that pulls dissolved gases out of the synovial fluid, just like the carbon dioxide that fizzes out of soda when you twist open the cap. Inside the joint, the escaping gases form a bubble with a pop. But the bubble doesn't last long. The surrounding fluid presses on it until it finally collapses. The bubble's gases scatter throughout the synovial cavity and slowly dissolve back into the fluid over the course of about 20 minutes, which is why it can take a while before you can pop the same joint again. Some scientists think there may actually be two pops, one when the bubble forms and another when it bursts. Popping a joint temporarily enlarges it, which may be why dedicated knuckle, neck, and back crackers say the habit makes their joints feel looser and more flexible. But you may have heard from a concerned relative or annoyed office mate that cracking your joints will give you arthritis. A doctor named Donald Unger heard this too. So, determined to disprove his mother's warnings, he cracked the knuckles of his left hand repeatedly for 50 years. While the right hand knuckles went unpopped. 36,500 cracks later, both hands were arthritis-free. For this selfless act of devotion to science, Dr. Unger received an Ig Nobel Prize, a parody of the Nobel Prize that recognizes wacky but weirdly fascinating scientific accomplishments. Unger wrote that his results should prompt investigation into other parental beliefs, like the importance of eating spinach. The jury's still out on that one. As for knuckle cracking, one study suggests that all that joint stretching and bubble bursting can cause your hands to swell and weaken your grip. But the biggest proven danger seems to be annoying those around you.
So we'll look at some of these terms in detail, the synovial joint especially. We'll talk about that in lab coming up as well as in lecture next week. With that in mind, just a couple announcements, and I've got a ticket out for you today. Remember that exam number 1 is a week from today. Remember that we won't meet here on Friday. Instead, you'll have time to take the exam wherever and wherever you would like. The details are here and are posted in your class program as well. Also, this is really pretty useful news. Some of you are getting some extra tutoring from Chase. Well, she is going to open things up, and every Tuesday is going to have a review session via Zoom, like a drop-in review session from 6 to 8 p.m. So you don't need to sign up in advance. You don't need to be there for 2 hours. Just a chance for you to come in and interact with her over Zoom, like an open session to ask questions. I will post the link to this on Blackboard and send it out in an announcement as well. But she was really wanted to make sure that I got the announcement out in advance of your exam next week, Friday. So check that out. It's a really great resource. It's free, and it will definitely help. So just to wrap things up here, you have your Friday Venn diagram. This is a good one. It's a little weird. There's no program for Monday. We are caught up. Actually, you're probably a little ahead on readings now. I assigned the readings for the joints. We haven't gotten there yet. You've got an exam to study for. No extra work over the weekend. So just note that there's no additional program for Monday. Also, one small note, my open hours Monday are truncated. I only have from 1 to 2. We've got this university-wide thing that faculty are going to from noon to 1. So I'll just be in the room for an hour on Monday afternoon. If you have questions outside of that time, of course, just shoot me an email and let me know. Otherwise, go ahead. I have a ticket out with a couple questions for you, and upload your diagram. Go ahead and finish that, and we'll be done for the day. I'll stick around if you have any questions. Thanks, everyone. Have a great weekend. It's going to be warmer than it's been.